Thank you, Kate. All right, let's see. Let's go into the pursuit of happiness. This is, as you can see, it's from the Modern Times movie by Chaplin. And I will be using actually pretty much everything that I'm going to be talking here today can be exemplified in Chaplin's movie. And what he means by modern times is basically in comparison to old times, where when we wanted to produce something, we basically had artisans producing shoes or whatever kind of commodities we needed to produce. And then everything changed with Henry Ford when he came up with a modern version, assembly lines, or the idea of assembly in a flow system, in a conveyor belt has been there for ages, but Ford really gave this modern structure that we came to know as an assembly line. You can see again Chaplin, and the idea of an assembly line is pretty much what we have in our mind. Everybody has seen or has heard about assembly lines, and the idea is that the product now is moving through a conveyor belt, and each worker is actually doing some of the tasks necessary for the product to be assembled. Pretty much different from what we had before, where a single artisan would work and do pretty much the whole product. I think the main important concepts are, by the way, I'm going to be talking about different types of assembly lines with some a mixed bag of results that I have, mixed bag of problems that I have worked with many colleagues of mine over the years. I haven't been working at this, well, I'm still working at this, so let me jump. But the main idea here is that you have the product going on, you have the different workers, each worker executes some of the tasks, and important as well is the fact that some of the tasks can only be executed after other tasks. So this gentleman here is probably doing something that needs to be done before Chaplin can effect his own task. I will put a little clip of this movie to exemplify one of the most important concepts. That is the concept of a cycle time, or basically how fast this conveyor belt can move. So I hope you can see this. So basically, the cycle time is the time that each worker has to execute his own or her own tasks. So you can see that, well, you want to maximize this cycle. You want to maximize production, which means minimizing this cycle time. You want this to go as fast as possible, but of course, you want each worker to be able to execute his tasks, not like Chaplin here, who is definitely running behind. Anyway, I really recommend that you watch the movie later. I will have some excerpts as well. But again, the idea is that you should balance this assembly line. You should divide the tasks among these workers such that each worker has time to execute what he needs to execute. Mathematically speaking, or modeling, talking in terms of models, what we have is a set of tasks that need to be executed. Some tasks, like task 9 here, can only be executed after some other tasks, 8 here as an example. And each task takes some time to be executed. And eventually, these tasks can vary according to the worker that is executing it. So Chaplin here was not really the most efficient, so probably his times are a bit larger than the other workers. In terms of modeling, what has been done, what is usually done is the fact that we do not consider the workers different anymore, but we consider the workers to be the same. So each task time is the same independently from the worker that is executing this task. And your goal is to assign these tasks, respecting these precedences, know that the product will flow in this direction. And any task that you assign here, or any task that you assign here, must have its predecessors, our task that it needs to be completed either here as well or in previous stations. There are two versions of the problem. One version is you want to, given a set of stations, you want to minimize the cycle time. Remember that this means maximizing production. Or given a fixed cycle time, you want to minimize the number of stations. These versions are called the assembly line, the single assembly line balancing problem, when you have fixed task times independent from the worker. If you want to minimize the number of stations given a cycle time, we call it type 1. And the other problem, minimizing the cycle time given a number of stations, we call that type 2. Here's an example of a solution. So I assign these blue tasks to this machine, these pink tasks to this machine, and so on. I'm dealing with the problem of type 2 here. So I have 4 workers, and I want to minimize the cycle time. Again, let's say that this is sharpening here. You need, he needs, in the cycle time duration, he needs to be able to execute all his tasks. And in this case, this is the station that's the most loaded. So the problem is to minimize the cycle time, ensuring that the precedence relationships are respected, and also ensuring that the cycle time is not smaller than the time needed at each station. I'm going to be talking a lot about modeling, so I will start with a nice result that we had a few years ago in terms of modeling. So this is a classical problem. So Bowman in 1960 already modeled this problem as a mixed decision problem. So the variables are xsi, so it's 1 if task I is assigned to station S. And these constraints basically mean that you assign all the tasks. This constraint is the cycle time one, saying that whatever time associated with the task that you assign to station S must be smaller than the cycle time if station S is open. So if the station is not open, of course, you have no task that can be executed there. And the most interesting constraints, these constraints are quite beautiful, the precedence constraints. Basically, it's saying that if I have a task and it has some followers, so the followers of task 1 are 2, 3, and 4, meaning that task 4 can only be executed after task 1 is completed. So the constraints are quite ingenious in the sense that what I'm doing here is that I'm looking for all tasks I, all followers of task I, and what I'm saying is that if I assign task J to station T, what happens is that in a station before T, I must assign task I every time I have IJ following this precedence relation. So it's quite ingenious. It's quite a nice constraint, but it's not the only way to model this. So for example, these ones are very, very popular and probably the most used or the most popular. They are very ingenious as well. So now I have task I and a follower J. And the idea here is that I'm summing. What I like about these constraints is that it's one of the few constraints where you see the index of a variable appearing multiplying the same variable. So what's here is that since you know that each task I will be assigned to a station S, so the sum of xsi for all stations is going to be 1, and it's going to be 1 in a given station S. And therefore, I'm multiplying 1 times S. So this term here basically gives the station for which task I is assigned to, and this one gives the station to which task J is assigned to. And if J must follow I, this number must be smaller than this number. There are also other constraints, but what we came up was these constraints here, which are basically the same thing. And of course, from an integer perspective, from the problem modeling perspective, they are all the same. They model the same idea. Here, the idea is that I'm looking again at ij. J is a follower of I. And I'm looking, if I look at all stations before a given station k, the sum I must be assigned, and also this sum must be greater than the sum of the same sum now considering J. So basically it's saying that, not basically, it's saying exactly the same thing, only that we show in this 2015 paper that these constraints are actually better than any of these constraints. So actually we show that Bowman is incomparable. You cannot compare to Patterson and Albrecht. These models are equivalent, and our formulation is actually stronger. And by stronger, I mean its linear relaxation is better. So we theoretically prove that these precedence constraints yield a mixed identity programming model that's actually stronger. It has a better linear relaxation than the other precedence constraints. For those who are not used to showing these things, these kind of proofs are quite interesting, and they just involve manipulation of these constraints. So it's algebraic, everything is algebraic. So in order to prove that these constraints are stronger than, let's say, this one, what we did was that we sum up all these constraints for all k, and then you end up here, and then you can manipulate these terms in order to come up with the Tangavlu constraint. And because I sum, the k here, I'm actually losing information. So even losing information, our constraints end up becoming the other constraints. So we can argue that these constraints are they actually are closer to what we call the convex hull than these ones. So this is just the idea, but just to show that these proofs are quite easy. They are just algebraic manipulation between these constraints. For those who are used to mixed integer programming, we know that in terms of linear relaxation, it's not just a theoretical result, but it can make really a big difference in the solution times for these mixed integer programming solvers, which are basically using the linear relaxation to give bounds and search the search space. So one thing is to be better theoretically, but we also show that these constraints, they were better from a computational point of view as well. So we tested these new precedence constraints on instances of the type 1, type 2, but also on all the problems. So in this table here, we compare our results with another formulation using all the precedence constraints of the beam packing problem with precedences. So these precedence constraints appear pretty much everywhere. And this is quite a short paper, but we are really proud or really happy with the results. But these are, as I said, the simple assembly line problem. Lots of simplifications here. In modern assembly lines, you have all sort of different situations or different practical requirements that you need to satisfy. One of them, one that I spent quite a lot of time working with, was the idea that these workers or these machines, they might be different. So again, going back to this table here, instead of considering that the task times are the same, we are considering that the task time depends on the machine or the worker that's executing it. Again, it can be useful for situations where we have robots of different generations or different robots altogether. But we worked mostly with this problem that was occupied my mind for quite a lot of time. That is the idea of sheltered work centers. In this case, in Spain, my main collaborator here was a Spanish friend, a Spanish colleague, who actually worked in these sheltered work centers. And the idea was that you had different people with different disabilities, and the time that each one executed the task assigned to them could be really different, going to the point that some workers could not or were not even able to execute some of the tasks. In this situation, as I mentioned, now you have different times for different workers for the same task. And the problem from a mathematical point of view, it becomes very, very interesting, because now you do not only have the assignment of tasks to the stations, but you also need to assign the workers to the stations. And the tasks that you assign here, the time that you need to execute them depends on the worker that you assign. So you have this kind of double assignment problem, and your objective is completely dependent on both assignments. So here's a simple model for the what we call assembly line worker assignment and balancing problem. The idea is not very difficult. Now you need to decide which task. You have variables that say if task I is assigned to station S and executed by work W. And here are old precedence constraints, and the model is quite similar to what we had before. In this case, I'm minimizing the cycle time. I could also be minimizing the number of stations. And I could use this model to the type 1 problem as well, but here I'm presenting another kind of model just to show how these things can be modeled in a very different way. So this was proposed by my colleague Reed and his PhD student at the time. And basically what I'm using as variables here are D, V, W, that are relations between two workers. So here I'm saying that worker V must come before or must be assigned to a station before worker W. And the way we associate, or the way that we create the precedence constraints now, is that we use some logical relationships. So now I say that if task I is assigned to worker V, so task I assigned to worker V, and task J is assigned to worker W, task J assigned to worker W, and if I and J, they have a precedence relation, it means that task worker V must come before worker W. So again, a very different modeling idea, but in my opinion, very interesting as well. So these are a bit of the modeling ideas behind this problem, and we worked with it for trying to propose solution methods and new models for different variants of the problem. So the first article that I want to talk about is this one, again, with my colleague Reed. Myron Moreira was my PhD student at the time, and Chaves is another colleague. And we try to solve this. This can be, as you can imagine, this can be very hard combinatorial problems. Actually, the simple assembly line balancing problem is already NP hard. So if you go to, this is clearly an extension of the solve, and it can be very hard to solve. So what we did was propose simple heuristics for this problem. Before I explain what these heuristics were, I'm going to go back to the solve quickly, because this idea of simple heuristics already existed for the solve. So the main idea is that you created some sort of priority index for your tasks. So you have some sorting of the tasks, and you try to assign the tasks to the stations following this order. Of course, they need to respect the precedence constraints. So this simple task here, or the simple priority rule here, is maximizing the time of the task. So I sort the tasks in terms of their task times. And what I do is, for all tasks that are available, I try to assign the task with highest task time to the station. In this case, the only task available now, or in the beginning of the line, is task 1. So I assign this task to the first station. Then these 3 tasks become available. I look at the one who has the largest task time, and I see if it can fit here. In this case, I won't be able to fit 115 plus 31 because my cycle time is 120. So I go to the next one that has a time that is available, that I can fit in this station. And if there are no tasks that I can fit, I just close my station and open another one and repeat the procedure. And as you can see, there are many, many different rules that can be applied. So for example, this one, I just looked, if I look, analyzing this task here, I look at the longest path between these and the end of the line, and I use this as my criteria for assigning this task in this constructive or greedy manner. Kate's probably going to be happy here because I had a master's student that just finished, and what we did was try to use Kate's methodology to analyze these rules, check if these rules were, which one was more efficient. Of course, in terms of average statistics, you could see that the task time, TDL was descending task time divided by the latest station. So the latest station that I could assign a task, and I would pick the task time and divide by this number. It was clearly the best. But we wanted to explore, for this large data set of instances proposed in 2013, we wanted to explore if we could have a better idea of the relation between these rules. So Kenya, I think she was here, so she did a beautiful thesis where she proposed many, many features to check or to establish or to characterize each one of these instances. She ran the Matilda methodology, and she found that these were the features that were selected. And there are quite some interesting results that she found. So for example, now I'm comparing, if I look at the graph, so first of all, the different classes from that data set, she could clearly differentiate between the different classes of instances. So each color here is one different class from Otto. But more than that, she could compare, for example, the TDL, that was the best one, with other rules. For example, the critical path one that I just mentioned. And it was quite nice to see that there were regions in the instance space that, even though TDL was the best in average, there were regions of the instance space where it was worth to use critical path. And not surprising, it had to do with the density of the precedence graph, the density of that precedence, the graph that represents the precedence relations. So this was a nice side result. But going back to the AWA, my student at the time, he wanted to generalize these priority rules for the double assignment now. And we have a problem because pretty much all those rules, or many of those rules, use task times. But the task times depend on the work that was assigned. So the first thing that we needed to do was to define worker assignment rules. So we proposed some also some greedy metrics in order to assign the worker to the station and then assign tasks. So it was kind of this double assignment implemented in a greedy fashion again. So first we assign the worker and then we assign the task. And we propose some different priority rules for that. The most effective one was this one, where basically we looked, okay, what's the price in terms of the future cycle time that I obtain if I remove this worker W from my list of workers. So if I'm looking which worker I'm gonna be assigning here, I'm basically saying, okay, I want to check why or what's the price that I need to pay for assigning this worker. What's this price, or what's a surrogate measure for this price for the remainder cycle time of the station was somehow given by the best time among the remaining workers for all the tasks that are not assigned yet. So if this value is very high, it means that if I assign this worker here, later on, there are tasks that I will need to pay a higher task execution time because this worker was actually the best one for this reminder tasks. So this is quite interesting, and the thing is that these are being used in many other situations. So it was a simple result that we are also very happy with. Another feature of the problem that we were interested in was the idea that you wanted to integrate this worker in the conventional job market. So it was nice to have these workers working in sheltered work centers, but the ultimate goal is to integrate these workers into the real job market. So in a very early paper, we already mentioned that even though it was nice, the true goal is to integrate these people in the conventional job market. And I'm putting this Commonwealth idea here because it was the first time that I saw the Paralympics being happening at the same time as the other games. So I think in the Olympics, you usually have the games and then you have the Paralympic games. But I realized that in the Commonwealth, it's not like that. They happen at the same time, which for me is ideal. Again, some modeling, very similar to what happened before, but now some stations will receive what we call conventional workers, and some stations will receive the workers with disabilities. And this was a simple way to model that. So each station should respect the task time, the cycle time, but the stations which had these special workers should respect not only the cycle time, but the increase in time associated with the extra execution times. As I mentioned, we developed some heuristics that were based on the heuristics that we had before. So the same idea of using these simple assignment heuristics were used here, but now you'd look at the line, you try to assign, you would ignore that you have heterogeneity, then you divide the lines and obtain a simple solution, a simple assembly line balancing solution, and then you try to integrate these workers within the line. What's interesting here is that for many of the problems, you actually had no loss in integrating these workers. So the number of stations that you needed, for example, to maintain a given productivity did not change. So each one of these rows here have 100 instances. And for example, in this row, we can see that 83 of these instances did not change. The optimal solution did not change, which is, we like to think of it as an assembly line being able to make the disabilities invisible. just with good optimization, you can make you can make this heterogeneity invisible to the line. This is something that Ford himself, he talks about in his autobiography. I don't think he was thinking about integrating these workers, but in any case, he mentions the fact that many tasks in the assembly line could be done by very, very heterogeneous workforce without loss. One thing that's also common is that you need to consider stochasticity. So going back to Chaplin, it's very nice to design a line where you have your cycle time and assume that the workers are going to always be able to execute that in cycle time. Even though in average they can, things happen. In any case, things do happen, and do happen not only in Chaplin movies, but in real life. So these task times here might not be as deterministic as we might want them to be, or we might consider them to be. So what we did in another work was to consider some sort of robustness for this solution. The idea comes from Beth Simmons, where we have this notion of uncertainty budget. So this UWI here, they are basically letting us know that you're going to have an extension, or this task is not going to be executed in that time that you predicted, but some more. And of course, not everything that is bad happening at the same time. So we create this uncertainty budget that says, okay, let's assume that things can go wrong, but they have a limit. It's not that I'm going to be taking longer for this time, for this task, and all of that. In average, you have some sort of stability. You have some sort of budget that you can think of what can go wrong. This again is a very, the modeling idea is again very simple, but there are some smart things coming from Beth Simmons in some sense that we use this. This is certainly a nonlinear equation. You have the variables, assignment variables here, and you have these changes in the task times. But using duality from this idea from Beth Simmons, you can actually linearize that and solve with this robust version of the problem with mixed integer programming solver. You can also have stochasticity. Because workers might not go to work. This was actually a very common situation in the sheltered work centers, because the workers, in particular, those workers had to go to medical appointments. There was a higher level of absenteeism. So in another work, what we did was to consider a stochastic version of the problem, using now the idea that in some scenarios, some workers would not be available. Again, you can see that the model is very, very similar, but now I'm assigning my tasks in a first stage and actually assigning my workers to the stations according to which workers I have available at each scenario. So again, we had some results on this. And another variant of this problem was the idea that sometimes you can move these tasks in the beginning of the day. As an example, you realize which workers are there, and then some of the tasks you cannot really move because they depend on tools or they depend on something that's particular to that station. But some tasks you can easily move around the stations, as far as we respect the precedence constraints. So this new version of the problem, we had some of the tasks as also some as recourse variables, as second stage variables that would be able to assign once the uncertainty was realized, once you knew which workers were available. The main goal here is to show that very different or somehow different versions of the problem can be modeled with very different, very similar models. Looks kind of confusing here because you have all these second stage variables, you have to write the constraints for each scenario, but if you dive in here, the idea is exactly the same. In another line of work, we dealt with job rotation. So the idea that you don't want that. You don't want the workers to be doing these tasks that can be very damaging from a physical sense. You want them to rotate between the stations and execute different tasks throughout the day. In Solve, in the simple version, it's very, very easy to do that because if I change this worker is executing some tasks here, and then I say, okay, you go to the second station and you go to the first station, nothing changes. They all execute these tasks with the same speed, if you like. But in the case of the work assignment problem, if I put my chaplain here, well, these task times here are completely dependent on the worker that I assign to the station. So now, by changing workers, you can completely destroy any sort of optimization that you have done in the line. And that was a very important problem in the sheltered work centers. Actually, the centers, thinking of this integration aspect, these centers, they somehow worked as schools. The worker was there, and he was, for most of the people that were worked in these sheltered work centers, this was the first time that they had a job. And I won't dive into the importance of having a job, into the importance of from a human perspective, but we all know how important it is. So we wanted, with the ultimate goal of having these workers move from the sheltered work centers to the actual companies elsewhere, what we wanted to do is to train these workers. So we developed a new objective function where we wanted to maximize the number of tasks to which each worker was exposed to. Again, with a sense of giving, of thinking of these work centers as a training period after which the workers would be incorporated in the normal or in the conventional workforce. So this was the main development in this paper, was just thinking about which metric should we use. And in collaboration with my colleague in Spain, he's actually a production engineer. So it was a very nice collaboration because I was pretty much working with the models and algorithms, and he had all the practical aspects of the problem that I had no idea, or I had very little idea. So working with him, we came up with this metric. And again, same model, only that now I have another index here telling me which period I'm talking about. So I'm now deciding if task I is assigned to station S to worker W in period T. And you have the different periods of your day. I won't dive into this, but basically we had a solution method that again was a combination of models and heuristics. So we used the simpler model in order to generate solutions that were improved or they were used to obtain the job rotation schedules. Later on, we tried to improve the results of this first paper. And in terms of methodology, it was quite interesting. The idea was we used a bunch of heuristics to generate, and we wanted these heuristics to be as diverse as possible, to generate good single period solutions. Then we would use a model to combine or to select among these many possible line assignments that we had, to combine different of these line assignments into a multi-period job rotation solution. And then my student Mario at the time, he worked with improving the solution that he obtained here using some sort of large neighborhood search. So you would, given a fixed solution, you would allow your model to change, to make slight changes, maybe to change one task from one station to a neighboring station, and so on. And after all these, we obtain a job rotation schedule. What else? Of course, you have all sort of different layouts or different configurations that you can have in these assembly lines. So another student of mine, Felipe, he worked with looking at different layouts. Looking at layouts, for example, where you have, and this is very common in practice, where you have parallel machines. So the product is coming here, and the first product that comes go to this machine, the second product that comes go to this one, and so on and so forth. The interesting aspect in this problem was to compute the actual equivalent cycle time here. So when you first approach it, the way we just thought, oh, that's simple, it's just the average of the cycle times, but that's actually wrong. So in order to compute the equivalent cycle time for these two stations, you actually need to do something like you do in electrical circuits. So the resistance is actually the 1 over the cycle time, the equivalent cycle time is equal to 1 over d cycle time plus 1 over d cycle time. And of course, this is not linear. As you can see, my thing is to do linear models. So he had to come up with a linearization of the model. And basically, he did this by switching the variables from measuring the cycle time to measuring the amount of products that you'd be able to produce here per minute and to produce here. And now we can add up these things. So if you produce 10 products per minute and 15 products per minute, now you know that the combination is going to be 25 products per minute. And so that was the idea of this linearization. I'm getting to the end. You also have, this is another student of mine, Pamela. What she did was to look at mixed models. This is an interesting problem. I just realized today that Kate worked with a little bit of this. The idea that in the line, you might have different versions of the same problem. So you might have cars that have 2 doors or 4 doors, and they take different times. So this in the literature is called mixed model assembly lines. And the interesting aspect here is that not only you need to balance these lines, but because the time of these, the time to execute the tasks change according to the specific task that you're dealing with, you have actually to sequence the products that you're gonna produce. So there is a stage where you're doing balancing, but there's also a later stage where you're doing the sequencing of the actual production. And she worked with this problem with the idea of minimizing the extra workforce that you need to use. So the idea here is that you start in this first station. It takes some time to produce this model, but then the next model takes longer. And if this time, considering where I started, goes beyond the limit of my station, I need to put some extra workforce here. And the goal was to minimize the amount of extra workforce that you needed to assign. I will skip this one in the benefit of time. And I'll just talk quickly about some more recent results that I had with my PhD student. Now it's a more actually, Adalberto is still doing his PhD, and he's been working with the same kind of problem in balancing assembly lines. But just to give you an idea of how these things can vary. So in one of his papers, he deals with the idea that now, on top of assigning the tasks, you also need to assign resources that might or might not be, but might be expensive. So you need to assign resources to the stations. And of course, the resources that you need to assign depends on the tasks that you have in the station. So there is another level of combination there, if you like. Another of his work is, this was when COVID came. And then what we saw was that we thought of social distancing. Actually, for many industries, what they had is that they had a huge drop in demands. Others have increased in demands, but some industries had drops in demand. And the basic solution would be to fire people. Well, you don't need to produce so much, so you just lay off people. And what the idea that he came up with was to actually implement this social distancing, but trying to maintain your whole workforce and trying to distribute the hours that you gave to each worker in some way in an equitable fashion. The advantage of this was, well, first of all, people wouldn't lose their jobs. So in the job keeper scheme that we had, for example, you could still maintain some the workers there working part-time instead of full-time. And the rest of the salary would be from some scheme like job keeper. But more than that as well, one day, we hope, life is going to go back fully to normal. And these workers, they kept their jobs and they won't need to be trained again. They're already there. So if you lay off people, if you fire people up and then you have to hire again, you have all the additional costs of training the new workers. So that was the goal of, that was one of his goals in this paper. And these latest results, he was looking at, again, the idea of multi-managed stations, which is very common when you're producing like large products like a vehicle. So you can have two workers working in the same station at the same time. And the models become also much more interesting in the sense that they're much more complicated. Now you have many combinations of workers and positions and so on. So that was another of his contributions. So I hope this gives a brief overview of what do people work with when they think about, when they optimize assembly lines. They are mostly thinking about balancing, sometimes sequencing, and most of the time trying to model the practical characteristics that you find in a specific industry or in a specific setting. Just as a very brief and very general conclusion, you probably heard of Maslow's hierarchy of needs. You need food, water, and then you go up in this hierarchy, being creative and spontaneous, like this gives you some sort of meaning to your life. But I'm citing Maslow here because he has a very interesting, very famous quote that you probably heard. If the only tool you have is a hammer, it's tempting to treat everything as if it were a nail. And that's a very common criticism for us academics, because we usually get stuck in our little field of work. And that's nice, that OPTIMA is here exactly for that, right? To bring these different capacities together. In the case of myself and my students, our hierarchy of needs in terms of industrial problems, it starts with very simple heuristic strategies. So that would be the food and water of our hierarchy of needs. And as you grow up, as you become more and more demanding, you actually go up to actually being able to model these problems and obtaining optimal or exact solutions for them. What is nice is that in this hierarchy, you can always be in the middle, right? You can always, and that's a bit of what I try to show here, is that the combination of using modeling and trying to solve problems with a guarantee of optimality can always be combined with simple strategies, bringing these hybrid strategies that can be easily applied. I think that's pretty much what I had to say, Kate.